unique history that Bob mentioned because my father's Elliot Steller. So I had a biological father, and he was in the field. And in 1985, I even wrote a book with him. But did I talk to him? No. I talked to Randy. So Randy's my academic father. And to someone who gets a doctoral degree and goes into the profession, that and Peter as an academic brother really are, in a way, very important. I don't want to really compare the biological to the academic family in a pejorative way, but it's very important when you come of age as a graduate student to have someone who you can look up to at a scientific and excellence and driving the thinking level, but also as a human being. So I think, Randy, I have to thank you from the bottom of my heart for creating for me, yourself, and with everybody else, including Peter and all the other grad students and postdocs, an academic family. Thank you.
And as we are academic siblings, I will also pay tribute to the academic mother, who has a large cadre of children and colleagues, and has always believed in us and supported us. And we will hear more about that throughout the day. So let's start with the first speaker, who is Brian Butterworth. And what we're going to do, everybody who's going to speak today has credentials and honors that are so long we could fill the entire program talking about them. So what we're going to do is make really, really short introductions. So please, if we leave out your many honors, excuse us for that. We're going to try and be short. So Brian Butterworth is Emeritus Professor of Cognitive Neuropsychology at University College London, and he's the author of the best-selling popular science book, The Mathematical Brain. You'll start to see a theme. His works on acquired mathematical disabilities and developmental disabilities, or dyscalculia, and his work has really helped to bring about a paradigm shifting, a cross-disciplinary approach, another theme you're going to see a lot of today, in understanding mathematical cognition using methods from neuropsychology, experimental cognitive psychology, developmental, neural network modeling, neuroimaging, genetics, and anthropology. Brian's recent work has focused on this mix of methods on understanding the causes and consequences of developmental dyscalculia, which he thinks is a learning disability that has been shown to be a more serious handicap for life chances of individuals than dyslexia, but it's not talked about very much. His recent work on fish, which you're about to hear about, is related to all of these objectives. Brian first got to know Randy and Rochel when they starred in the concept of number and simple arithmetic meeting that he organized at the Scuola Internazionale Superiore di Studi Avanzata in Trieste in 1994. This meeting was one of the first to envision a truly multidisciplinary and multi-species approach to mathematical cognition. They were inspiring, he says, and we all learned a lot from them. Much later, Randy tried to teach Brian how to ski moguls, and this was one of his few failures as a teacher. Brian, please.
Right, thank you very much. That introduction. It's a great honor for me to be here. It's also a great pleasure. And let me start with a little personal story. Many years ago, I was invited to apply for a chair at Piaget's old department in Geneva. And in those days, I was a psycholinguist, and I gave my usual stump speech on speech production, speech comprehension. And things seemed to go fairly well. But the person who invited me knew that I had a background in the philosophical basis of mathematics, the foundations of mathematics. And I was asked, what do I think of Piaget's approach to the foundations of mathematics? And I said something like, I guess I said something polite, you know, he's a pioneer, it's really interesting. But there were a couple of young guys in America just published this really interesting book called The Child's Understanding of Number. And it seems to me that this is more consistent with what I know about the foundations of mathematics. And so, also, it suggested that kids have a sense of number much younger than Piaget had envisaged. And also that in this book, they had separated the number domain from other aspects of cognition, which again I thought fitted in well with, for example, Piaget's axioms, where numbers are taken as a given, and the logic that you use applies to the numbers, but you don't derive the numbers from the logic. Finally, and I don't think I've said this, the great thing about the child's understanding of number was that it's beautifully written, I can understand it, of course I understood it, and I didn't have quite the same feeling when I read Piaget. But I think even then I was too polite to say that. So, given that, let me start by a post-Gödelian. I did some early work on Gallistel. A post-Gödelian evolutionary Neoplatonist, or what I learned from the child's understanding. There's a picture of I mean, one of the things I thought was wrong in Geneva was that they were somewhat enthralled to the logicians. And so I call this the lure of logicism. So, Piaget seemed to believe that the concept of number is derived from reasoning, classification, transitivity, seriation, and so on. And this would exclude all non-humans from possessing a number concept, which seemed to me to be a bit strange. By non-humans, I include infants. And actually, my very first experiment in this area, when I was an amateur, dilettante, was with a baby of 1 month old. We came into possession of this baby, who for the purposes of this talk I'm going to call Amy. And I had read a paper by Prentice, Starkey and Cooper showing that infants of 5 or 6 months could actually make numerical discriminations. And two things struck me about this paper. A, it was pioneering. B, it wasn't done right. It wasn't done right in 2 ways. First of all, I didn't think he controlled the stimulus properly. And secondly, I thought, well, if it works for 5-month-olds, why shouldn't it work for 1-month-olds? Particularly R. And so we programmed an experiment in which, this goes a long way back, we used a 32K BBC computer. 32K. We programmed this in BBC Basic. And you had a green screen. And so you would see lighter green squares on a darker green screen. And we had, the way we designed it was that all the variables that we could think of, like the total luminance, the amount of edge, the position of the squares, they were all counterbalanced in a long sequence of the experiment. And what we were going to do at the end, we were going to do an analysis of variance in which we would see where that number came out as a significant factor. But you had to do the whole sequence. And we used to have knackers delivered in large cardboard boxes. So we strapped Amy into the chair, put her inside this cardboard box, and all she could see was the screen through the screen. But we didn't use the method that people use these days, which is looking at habituation. Because I was a psycholinguist. Psycholinguists aren't interested in looking, they're interested in hearing. And so how do you know whether the child is attending to hearing? By their sucking rate. So you do sucking habituation. So we had this teat in Amy's mouth, connected to a pressure transducer, which was connected to our little computer. And so we put Amy in this thing, and she was looking at two green squares, 2 light green squares, 2 light green squares, 2 light green squares, 3 light green squares. And so the sucking rate would go. And then, as we changed the number, great. And it was all printed out. I don't know if you remember this, the old ones were what you will remember that they had these printers with holes down the side. And so we had just one line, but we had paper that wide with holes down the side, and come out and fold out. And Amy was doing just great. Actually sucking more when we changed the number and sucking less as the number was repeated. The problem was, halfway through the series, she refused to have this teat in her mouth anymore. And nothing we could do persuaded her to put the teat back in her mouth. So I kind of abandoned doing infant work, because I wasn't really trained in it, and no one would lend me babies. But that was the first experiment I did, and it confirmed me in my suspicion that Rochel and Randy were right, that babies under the age that Piaget had suggested actually did have a sense of it. So anyway, I thought that Piaget was perhaps too impressed by philosophical logicists. So, for example, Frege, who was a philosophical logicist, in his Begriffsschrift, wrote, I first had to ascertain how far one could proceed in arithmetic by means of inferences alone, with the sole support of those laws of thought that transcend all particulars. My initial step was to attempt to reduce the concept of ordering in a sequence to that of logical consequence, so as to proceed from there to the concept of number. And when he says laws of thought, he doesn't mean how we actually think. What he means is essentially the laws of logic. Russell, in the introduction to Philosophical Principles of Mathematics, says, the present work has two main objectives. One of these, the proof that all mathematics deals exclusively with concepts definable in terms of a very small number of fundamental logical concepts, and that all its propositions are deducible from a very small number of fundamental logical principles. In fact, even some Piagetians, as some of you will know, trying to axiomatize the development of number in this kind of logical sequence. Now, Gödel showed this project ran into some serious problems. I'll have to talk about that later. I mean, one of the things he showed was at least that any provably consistent axiomatization will not be. But the point that occurred to me was that Russell's project was not an epistemological one. Rather, it was the search for certainty. He wanted to ensure that mathematical statements were true, not how we come to know them. And in fact, if you read Russell's autobiography, you'll see that one of the things that motivated him even as a child was certainty. He wanted to know how he could be certain of certainty. So, maybe knowledge of numbers is not derivable from logic. Maybe they constitute a separate domain. Now, I actually came to this as a neuropsychologist. And neuropsychology is actually a very good way of finding out. You need to have a very strong theory in which you specify the necessary and sufficient conditions for somebody to be able to do something. Then you find a patient who lacks one of these necessary and sufficient conditions. And your theory should predict what that outcome should be. So the question you can ask as a neuropsychologist is reasoning ability sufficient for arithmetic? Is it even necessary for arithmetic? So at the time I was working in the National Hospital for Neurology with great neuropsychologists, foundational neuropsychologists, Elizabeth Warrington and Tim Shanis. And I wasn't working on numbers and arithmetic, I was working on language. But then I had a student, a very brilliant student, who wanted to come from Italy to London to work on aphasia. When she got to London, she said, I don't want to work on aphasia, there are lots of people working on aphasia, I want something else. So I thought back to my reading of the child's understanding of number and my own work in the foundations, and I thought, what about acquired acalculia? No one's working on that. In fact, there's very little of that. I mean, I've had a look at the literature. You could probably read the entire literature in a couple of weeks, which was probably an overstatement. You could probably read it in a week if you were quickly. There was very little done. Of course, now there's an enormous literature, a much larger literature. So we started to work on acquired calculator. And that, by the way, was the golden age of neuropsychology. You could see a patient in the morning. If you were working with a really brilliant clinician like Warrington, you would develop a hypothesis about what this patient could do and what the patient couldn't do. You'd have lunch, design some new experiments, come back in the afternoon, test the patient formally, write up the paper in the evening and send it off to the brain. Now, we didn't quite do that with our first paper. This actually took a bit more work. These are some of the dissociations that we identified early on. So the first patient, at the top of the list here is CG, which my student listed. CG was a woman in her 50s who had run the family hotel in northeastern Italy. She kept the books in the hotel. She had a stroke which affected her left parietal lobe. And when we saw her, her numerical abilities were the worst that had ever been reported up to that point. And in fact, I've never seen a patient who was so severely acalculic reported since. So to give you an example of her numerical abilities, Lisa would ask her to count the number of objects on the table. So she'd put out, let us say, 5 objects. Very simple task. So she'd say, Signora, can you count these? Signora, 1, 2, 3, 4. She'd point to the 5th one and say, La mia matematica finisce qui. She couldn't go beyond 4 in any of the tasks that we gave. We gave her lots of different tasks to see if it's the words that we were using, or whether it was the symbols, whether we were comparing dots, whatever. She couldn't go beyond 4 line. And in fact, she didn't even recognize the names of the numbers of words above 4. Nevertheless, her reasoning was entirely intact. We used Piagetian reasoning tasks like transitivity, seriation, classification, all the classical tasks. She was absolutely flawless on these. And that demonstrated to us that having these logical abilities was not sufficient to have a normal concept of number. We also found double dissociations because we were looking for it. So patient IH, who was one of Michael Kopelman's patients at St. Thomas's Hospital, he was the opposite. He had no language. We couldn't test his reasoning. But his language was almost completely gone. He had dementia, progressive condition. So he was a chance on object pointing. So he'd say, point to the orange, he was a chance. We'd ask him, his speech was just a few stereotype phrases, but he had intact autobiographical memory. But his calculation, if you gave to him written for multi-digit multiplication, division, he was flawless. The other patient I want to just briefly mention is MRF. The MRF was presented by Warrington, one of her Thursday morning case conferences. And so there's a kind of standard format that Warrington used. One of them was a digit memory task, short-term memory task. So she asked the patient to repeat back the following numbers: 1, 2, 8. The patient got 1, 2, couldn't do 8, and in fact he couldn't reliably do more than 3 digits, and sometimes he couldn't even get that right. Now, because Warrington had developed what she called a graded difficulty arithmetic test, which many people still use, she also asked him to do the following calculation. Remember, he can't repeat back 1, 2, 8. So what's 128 plus 149? So what is 128? What's 119 minus 35? He could do that. He was at the 63rd percentile on Warrington's graded difficulty arithmetic test, even though he couldn't reliably repeat that more than 3 digits. In fact, he wasn't very good at 3 digits. And we had terrible trouble getting this paper published, because everybody thinks that working memory is absolutely crucial to being able to do arithmetic. We did get it published. And what we concluded from this was that there's a separate, a domain-specific memory system for numbers. If you ask people to repeat back numbers, what you're asking them to do is use a phonological memory. If you're asking them to use numerical memory, then they can do it. Now, okay, you've got a separate domain of numbers, but what about the epistemological problem that arises with the domain of numbers? So this is the epistemological problem. How do we know about mathematical objects if they're abstract? And numbers are certainly abstract. Now, Plato himself didn't actually deal with numbers, he dealt with geometry. He pointed out we never encounter a perfectly straight line or a perfect triangle. We only encounter imperfect instances. Hence he developed this theory of Platonic forms, which I return. In the case of numbers, the situation is actually more acute. At least in geometry, the actual instances that you encounter are similar to, in some sense, to this Platonic form. But in numbers, how can they be? Because, 3 coins in the fountain and 3 wishes, what perceptual properties do they have in common? They don't have any perceptual properties in common. So they are really very abstract. But what is their threeness? Every collection of 3 things is different. Threeness is an abstract property of the same. And abstract objects, abstract properties, can have no causal status. They're not part of the material world. So how do we come to know them? Plato's answer was anamnesis. So, what he puts in the minds of Socrates is his avatar. Socrates argues that the soul is immortal and is repeatedly incarnated, and that knowledge of geometry is there from eternity. And so when you think you're learning something, what you're really doing is you're trying to remember what was in your soul already. Now, clearly there are some sorts of knowledge which are not meant to be like that, contingent knowledge, like the way from the highest hotel to the fiber optics lab. But for these serious types of knowledge like geometry or arithmetic, we're remembering them from another life. Now, I think it has to be said that anamnesis is no longer one belief. But how about an evolutionary version? In the case of numbers, have we evolved a mechanism for dealing with numbers in the environment, representing them and operating? Well, this actually seemed consistent, at least in my reading of the child's understanding of numbers. So I thought it was possible that one could have an evolutionary account, even though in the book, as far as I remember, there isn't an actual evolution. What they proposed were new models. So first of all, they separated number from general quantity. And they said that we need to think about 2 types of things: number abstractors and reasoning principles that operate on these number abstractors. They also distinguished between 2 types of estimation: exact and approximate. Sometimes you need to know exactly how many things there are, sometimes you don't. Like, for example, I could make an estimate of how many people there are in the room, or I could count. Depending on what I actually want to do with that information, I might use one or another. Now, of course, arithmetic depends on exact representations. So they say the use of unique tags in the mind to mark or tick off the items in a collection is intrinsic to the counting process. These tags have to be in a fixed order. The tags must have an arbitrary status. They cannot be the names or descriptions of the items in a collection being counted. That's very important. So they have to apply to any things that you want to count. So they're consistent with the idea of numbers being the abstract property of the set. Now, the tags they called numerals, and counting words they called numerals. Is that how you pronounce it? Numerals. And they also said numerals need not be the numerals. That is, you don't need to have counting words in order to do counting. And that, of course, opens up the possibility of an evolutionary account, because really people have numerals. They also had some anthropological lessons. So they referred several times to methods of counting that do not use or even forbid using the counting word sequence. Though the book doesn't refer to languages without counting words or counting word equivalents. Now, it turns out there are quite a few of these, and they're what commonly calls restricted communal bases. So some languages still exist in remote places that count in twos and only up to about 10. So you go 1, 2, 2, 1, 2, 2, 2, 2, 1, so on. And a few of those still there. I mean, the reason there aren't more of them is because people with 10-base system tend to kill people with the 2-base system. Anyway, so there are well-known examples of Amazonian languages with restricted counting word systems, for example, the Piraha and the RuCCS. And it's been argued that not by Gelman and Gallistel, the opposite view, that without counting words, numerals, it's not possible to understand exact counting numbers. This is just a map of languages with severely restricted numeral systems. They're the ones in white, so there's some in Australia, quite a few in Amazonia. I want to talk about Australian examples. Most Australian languages are restricted. So Walbury, which is very well studied, has words only for one, two, few, and many, and they don't have any other way of counting. There's no recorded instance of counting in some other way. So, for example, in New Guinea, where they don't have specialized number words, there's quite a lot of body part counting. So they say left little finger or right elbow instead of saying 1/17. But Ken Hale, so this is from Bob Dixon's book, The Languages of Australia. The Bible of this was named. And he writes that Kenneth Hale has commented that the English counting system is almost instantaneously mastered by the Walburys, who enter into situations where the use of money is important, quite independently of formal Western-style education. So, how can this be if counting words, numerals, are necessary for understanding numbers? Could it be that the Walburys possess numerals and map them onto English counting words when they managed to get home? So, do we really need counting words to count? Remember, numerals need not be the number ones, numerals. So here's an early example from Amazonia. This actually comes from John Locke, English philosopher, writing in 1690. So the Tupinambas, a tribe from the depths of the Brazilian jungle, had no names for numbers above 5. But they could reckon beyond 5 by showing their fingers and the fingers of others who were present. So this is an example of people who didn't have a lot of number words, but nevertheless had concepts of numbers beyond the number words that they actually knew. And what Locke argues is that counting words are not necessary to have these concepts, but they're helpful. For without a name or mark to distinguish that precise collection, it will hardly be kept from being a heap in confusion. And distinct names of different numbers conduce to our well-reckoning. And Rochel and I have discussed Locke some length in a paper we published a few years ago. Let me tell you about the work we did with some Australian Aboriginal kids. So, I mean, Ken Hale's remark is an anecdote. It's not proper science. It was a linguist, not a proper scientist. No, sorry. Please have that scrubbed from the record. But, so we tested a couple of different languages. One called the Walbury, that's a Central Desert language in a place called Willara, and the Diablo, which is a language isolate. It's not related to the other Australian languages. But that doesn't have, it doesn't have number words really above 5, and you're not introduced to them until you're an adolescent, because the number words that they do have are only used in particular ritual contexts. So let me give you, those of you who haven't been to remote parts of Australia, let me show you what it's like to get out of the lab and do some field work. So you come across these kinds of images carved on rock faces. This is a Quincan Dreamtime creature. Here's another Dreamtime creature. I mean, it's really fascinating going in. It's great. The important thing, though, is not to go during the wet. And we don't. And not only is it you get bogged down, also people are not really very friendly. So this is the Central Desert site, and this is our researcher, Derek Lloyd. This is Derek on the Wichita grub hunt, and you can see the child over here has been eating a Wichita grub, which is the larva of a flying creature. So it's a bit like, I suppose, I'm a scientist, get me out of here. So of course, Derek actually has to eat the Wichita grub. The other site is off the coast of Arnhem Land, on Groot Island, at a little settlement called Anguru. And let me just show you what it's like doing this kind of work. This is Groot Island. It's an island, so there's a lot of fishing. There's some fresh water. Is that it's this. So those of you who just work in labs, I just want you to know that collecting this data can be somewhat problematic. So here's a croc. They're very nimble, these crocs. But we did learn a lesson locally, which is don't be the first one in the water. So here are some of the tasks that we used with our subjects. So we had we used only monolingual speakers of Walbury or Vidiagua. Our researchers would learn a bit of these languages, but they weren't fluent speakers. So we in general used somebody who was bilingual to help us, or nearly bilingual. And this, we did some classic number development tasks, identifying numerosities across modalities, because we wanted to ensure that that concept of number was abstract, so it didn't matter whether you saw some objects or you heard some objects. And some additional tasks. So this is the basic setup. This is Fiona. This is our interpreter, and this is our subject. And you can see this technologically advanced. We have 2 maps here and some red counters. So this is the memory for counters task. Fiona puts out, in this case, 5 counters. Then she covers them up. And then the subject has to put out the number of counters that she saw. Now, of course, you can't ask her to put out the same number of counters, because they not only don't have words for numbers, they don't have a word for number either, so you have to try and show them what you mean. Non-verbal addition, again, it's a classic task. This is, so that's the interviewer's map, that's the child's map. So the interviewer, experimenter, puts out some counters, covers them up, then has 2 more counters that go under the mat, and then the child has to put out the same number of objects as are now under the mat. Cross-modal matching, so Fiona would bang 2 sticks together. Again, you see this high-tech work, and then the subject had to put out counters corresponding to the number of bangs that her. She's doing. Now, this is some of the data. So we also had a comparison group in Melbourne who were brought up speaking English. So red are the Walbury speakers, blue are the Aggie speakers, and green are the English speakers. Along the bottom is the set size that the person has to try and reconstruct outside of what the actual responses were. And as you can see, there's not much difference. That statistically is no difference between the three groups of children. This is cross-modal matching. Again, you get quite good performance, and there's no difference in the performance between the three groups of children, the English speaking, the Walbury speaking, and the Aggie speaking. And this is addition, more variation here. Here, these are kids 4 to 7, but again, there's no statistical difference between the three groups. However, in the task like, in the memory for counters task, there was a very important difference between the Aboriginal kids and the kids in Melbourne. What the Aboriginal kids did, they had a strategy which was to try and reconstruct the pattern that the counters had been put out in. So we just noted down whether the child copied the pattern they'd seen or didn't. So it turns out that the children in the Northern Territory, the Aboriginal children, tended to use, trying to copy the pattern that they'd seen, whereas the children in Melbourne never did, because they had this counting, these numerals, which they would use. So anyway, it shows that children who don't have number words in their language can nevertheless do tasks, at least up to the age of 7, as well as kids who do have number words. So what kind of mechanism could they use? Of course, humans have many ways to do it. Our Australian children found spatial strategies for solving our counting arithmetic task. But is there a simple counting mechanism, as Gallistel has suggested? I can't remember where he suggested it. Maybe in several places. So here's an example of a simple counting mechanism. Costs less than $2. So what you do is you just click down for each thing that you're counting. The difficult thing, the thing that needs a lot of brain power, is deciding what the thing is. So for example, if I wanted to count the number of females in the room and the number of males in the room, I'd have to have some quite high-level cognitive skills in order to distinguish males from females. But the actual counting process is just clicking. So the key is normalization. So think of the clicker used by traffic counters. One click for each vehicle, one click for each car, one click for each lorry. The problem is deciding what's a car and what's a lorry, not the actual counting process. So here's something that Randy and Rochel have favored as an accumulator mechanism, which would be by making a church. So you have one cup per item count. It doesn't matter what the item is, just put in one cup of liquid into your accumulator. And then, if you want to remember it, you can tip the accumulator into it. The critical thing here is that it's one cup for each thing, whatever that thing happens to be. So you can look at it in a slightly more scientific way. So this is the way Methodist Church described it. You've got some kind of pacemaker in your head, and you open a gate whenever you see an object, and then some energy goes into the accumulator. And this is a similar kind of idea from Stanislas and Changeur a long time ago. So here's the normalization process, what they call a location map, and there's an accumulator. Then they map it onto another way of representing the number. Now we've explored this because we're interested in representations that will support arithmetic. And so we've done some modeling. So there are various kinds of ways you might think of number. One of them is to have a barcode. Another is to have a number line on which each number is represented, and there's been a long argument between DeHaan, for example, and Randy about whether you should represent these things on a compressed representation, a linear representation, and then there's the numerosity code, we call the numerosity code, in which Randy and Rochel called histogram, so histogram repeating, so you're adding these two things together and just together. So in your modeling, there are certain desiderata. So the representations of exact magnitude should encode three crucial semantic features: a cardinal meaning, how many things there are in the set; one-to-one correspondence between elements of the external, of the internal representation, elements of the external set counting, and a format that affords arithmetical operations in a simple and intuitive way. And Leslie, Gelman, and Gallistel also make a similar point. Number concepts must support arithmetic inference. It is crucial that potential symbols for numbers support arithmetic inference. This means that to be a number concept, a symbol must denote an entity over which arithmetic operations functions. So this is what we did here. We had a representation, it's a histogram representation. So 5 is represented by 5 units in our neural network, 3 by 3 units in our neural network. So it corresponds to our desiderata. And this is the solution to 5 plus 3, it's 8. Now, the network has to learn what that solution is, and we use contrastive divergent learning. I'm happy to talk about this in discussion if you're interested, but it doesn't require you to plan the inputs and the outputs. So the system settles into, if you like, its lowest energy state, and this process is repeated over and over again, and then you plant the inputs and you see if it produces the correct answer. And this is the data we wanted to model. So it's very easy to get any kind of computer to do addition, right? Dead easy. But we wanted it to do it the way humans do. And one of the things that we know is that when humans do addition, there's a problem size effect. It's what everybody finds. It's been known for years. It's a very, very robust, reliable finding. And so the larger the sum, the longer it takes you to produce that sum, however you might do it. So this is the data we had from an experiment we did a long time ago. These are, you probably can't see it, but this is for each pair of numbers between 0 and 9, and how long it takes you to get the answer. And so as the sum increases, so it takes you longer to get the answer. So this is what we're modeling. This is a paper we published. So we're using what's sometimes called strong inference. That is, we use the same network, but we had different assumptions about what numbers look like. So we had a barcode, we had a compressed number line, and we had the numerosity code. And we also had a symbolic code, where each number is independent of all the other numbers. It's just the representations you can follow. And so what you can see is when we use the same network, the same learning algorithms, but different assumptions about what the numbers look like, what their properties are, none of these representations actually gives you anything like the correct solution. Whereas numerosity coding, gives you something which is very much like the actual real human data. It doesn't quite capture ties effect. So 8 plus 8 is retrieved more quickly than 9 plus 7. For reasons we can discuss, we have a theory about that, which no one believes. So I'm very happy to discuss it. So we thought numerosity coding is a way of thinking about representation of numbers. So the question then arises is, are we born with a set of numerals, or do we construct them online? And we have to go back to Locke here. So, I mean, although most of you think of Locke as an empiricist, he actually had some rather nativist tendencies. So he said the simplest idea is that of one. We don't get this from experience, we seem to have it innate. And this can be repeated by adding repetitions together. Doing that, we get complex ideas of larger numbers. Thus, by adding 1 to 1, we have a complex idea of a couple, and so on. And we should give each complex idea a name or sign whereby to know it from those before and after. This again is his idea that having names is useful, but having the concept doesn't depend on having the name. It's just how you use it subsequently. For without a name, that would be confusion. Distinct names conduce to our reckoning. The addability of numbers gives us the clearest and most distinct idea of infinity. And of course we know that Rochel has looked at concepts of infinity in very much. We'll go there today. So this idea seems to have been revived by Western Gelman and Gallistel. So they say the concept of one is innate, the adding mechanism is innate, and there's an identity function which Locke mentioned. And there's an accumulator mechanism which is locked and specified how adding is done. So the question is, can this very simple mechanism be found in creatures without much reasoning ability and without much language? For example, fish. So fish have only 1 million brain cells compared with the human. Well, these are small fish. 80 billion brain cells, so this is the sorts of fish that we deal with. They swim around in shoals, and by swimming around in shoals, this actually reduces the risk of predation for each individual fish, and also helps them with foraging. So the first question we wanted to ask was, do fish scientists? That is, do they have a special mechanism for dealing with small numbers? Now, summatizing is quite a controversial issue. There's some people who believe there are 2 mechanisms, some people who don't believe there are 2 mechanisms, just one mechanism that you use for the whole range of numbers that you numerosities that you encounter. I now think there are 2 mechanisms. We did a neuroimaging experiment in which we found different activations in the small number range, the large number range, if you do some fancy sorts of control. Again, I haven't talked about it for interest. And what we wanted to compare with normal-sized Italian students. So this is the experiment we did with humans, is that they saw 2 displays of dots, and they had to decide which one had more in. And if the dot range was 1 to 4, there was no effect of how similar the numbers were. So 4 against 3 is as difficult or as easy as 4 against 1. I know Randy doesn't believe this, but we can again talk about that. However, beyond 4, you do get a ratio effect in both accuracy. Accuracy goes down. So if one numerosity is 75% of the other, then you're not so good, and you take not correct judgment. Okay, now, it's true that we didn't have our Italian students swimming around in tanks, and we did have the fish swimming around. So there is a difference between these 2 situations. I hope you'll see the fish behave in a rather similar way. So we've got our subjects in the middle here, and the subject can see some fish on either side, and we want to know which way the subject will swim. And the idea is that in nature, fish will swim to the larger shoal if they're shown fish. Okay? So what difference in the numerosity of one side and the other side can the subject fish with only 1 million brain cells actually discriminate? So does it show a ratio effect for larger numbers and no ratio effect for smaller numbers? And does it depend upon how experienced the fish is? So, newly born, newly hatched fish, or experienced fish used to swimming around with experimental tanks. So this is the data. So this is small quantities, and these are the different ratios. This is 1 versus 4, this is 3 versus 4. And you can see, and this is accuracy, we didn't use reaction time of the fish. So this is accuracy, there's no difference between 4 versus 3 and 4 versus 1. But when you get larger quantities, you do get a ratio effect. So they think they have 2 different systems. Actually, they're not very good when it gets to 75%. 3 versus 4, 75%, they basically are a chance. Bear that in mind. They can also identify numerosities. Now, this isn't research I've done, but my colleagues in Harvard have done. So this is the situation. So this is fish swimming around an experimental tank, this time not. So that's experimental tank. And over 2 exits to the tank, there are some symbols. And the fish is trained by feeding it near those symbols. And we can vary the sorts of symbols that we use. So we might train what they say. So, for example, you might reward the fish for going to the gate with 3 symbols, but it could be a different 3 symbols that the fish then has to use in order to get the reward. And the fish can do this quite well. This should be a fish trained. Now, of course, these are all displayed simultaneously, but in order for them to really have a concept of number, it shouldn't matter whether the set of objects is displayed simultaneously or successively. So this is another experiment that the Padua group has done, where the fish, the subject fish is in the middle here, and the fish can only see 1 fish at a time because of the way in which these backwards are set. So it might see 3 over this side and 2 over this side. You can only see them 1 at a time, so it has to kind of accumulate each example. Now, of course, I don't know how the fish knows whether there are 3 fish there or 1 fish swimming. I mean, maybe fish know less or more. Anyway, but they only done this with very small numbers. So there is some evidence for sequential enumeration by fish. Now here's an experiment we published recently, which we have up at the top. This is the title of the paper. Collective enhancement of numerical acuity by meritocratic leadership. Now this is actually based on a human experiment that we did. So again, it's a number experiment. And so what 2 individuals have to do is they have to decide whether there are more yellow dots or more blue dots. Okay? They make this decision independently. And then without continuing to see the stimuli, they then discuss, if they make different decisions, they then discuss the decisions that they've made, and then they have to come to a joint decision. And what we found was...
Do they get feedback?
We've done it with feedback and without feedback. Okay? What we do know is that they have to be fairly similar in their ability to get collective enhancement. Okay? So if you've got one is very good and one is very bad, you don't get collective enhancement. They have to be similar. And in that case, after having talked about it, the joint decision is better than the individual decision. So naturally, I thought, this is for humans, what about the fish? Okay, now we know the fish go wrong, but it's not clear that they actually converse. So this is the experiment we did. We have the same basic setup with a subject tank and a fish on the other side, and we tested each fish individually, and then we put two fish together to see if you get collective enhancement. In terms of the ratio that they discriminate. And what we found was, yes, you do get collective enhancement. They can now discriminate 4 against 3 in 75% of the way that they could before. If you just take the average of the two fish, that's like the average of all the fish. But if you put two fish together, they actually behave like the better of the two fish. So what's happening here is meritocratic relationship. That is, the fish that's not so good follows the fish that's better. So this is a very naturalistic situation. We also did a training study with larger numbers here, and again we compared how well the fish does as a singleton and in a diet. Again, what we found was that you get meritocratic competition with fish. So the fish do better when they're together than when they're separate. And this, by the way, there's a theory about why animals work better together, and it's sometimes they make better judgments when they work together, sometimes called the many wrongs theory. So what you get is you assume that each individual in the group has a particular error. If some make an error that's too big, some make it too small. If you put them together, then you get something close to the right answer. But here, you've got a different. This isn't the many wrongs theory. This is a quite different. This is meritocratic. And of course, we now know, because of brilliant work by, for example, Liz Brennan here in the audience, that you get numerical abilities of the species in primates, chimpanzees, monkeys, other mammals, cats, dogs, rats, and so on, reptiles, fish, of course. And also there's some evidence of counting in insects, in bees particularly, but also recently shown in ants. And ants count the number of steps that they make in order to do path integration. So if we've got all these different creatures who are seem to have a numerical ability, creatures with very little brain, almost made a political comment there on my update. Creatures with very little brain. So it must be a very simple mechanism. It's a really simple counting mechanism. It's rarely as often a problem. So, but, of course, we're much better at these number tasks than these other creatures. So why are we so much better than other species? It's because we have cultural tools. So counting words, as Locke said, conduce to well reckoning. This is what Whitehead, collaborator with Russell on the Great Logicist project, says: by relieving the brain of all unnecessary work, a good notation sets it free to concentrate on more advanced problems. It, in effect, increases the mental power of the race. A bad notation can create problems. So, for example, Greek numerals, Hebrew numerals, and Roman numerals, not very good for doing trade. And in fact, when people who had these writing systems traded, they actually didn't use it to do the calculation. They used counting boards, which were divided up into units, tens, and hundreds. Here's an example of a bad notation. This is one of the very first dyscalculics we ever saw. This was one student who came to see my partner, Laura. And she was really smart. She was a psychology student, is that right? So she must have been really smart. And we thought that 8 plus 4 was 15. I think, I'm not sure. And she had a way of doing this, which was a way of doing her calculations, which depended on having a mental number. And this is her mental number. 1, 2, 3, 4, 5. Right. And then the next bit of the equals to 10. 5, 6, 7, 8, 9, 10. what about beyond that? That's 10 to 20. So she gives this, but of course the thing is 5 is repeated twice and the decade's repeated twice. Diana pointed this out. The student got much better, but then wouldn't come in for tests, so we don't know quite what happened. But having a good notation is a big advantage. So here is Leonardo of Pisa. Do you all know Leonardo of Pisa? Also known as Fibonacci. Leonardo of Pisa wrote a very influential book called the Liber Abaci, or the Book of Calculation. And in this book, he promoted what's sometimes called Arabic numerals. And down the side of the page here, you can see Arabic numerals with their Roman counterparts in there and their names in Italian. And because of Leonardo of Pisa and the introduction of Arabic numerals in Italy, and also the development of double-entry bookkeeping, people from all over Europe came to Italy, particularly to Venice, in order to study these new symbols and double-entry bookkeeping. And this is a picture of the Fonda Tedeschi. This is where German tradesmen would send their sons, all of their sons, to Venice to learn about Arabic numerals and double-entry bookkeeping. This lovely building is now the post office in Venice, just by the Alto Bridge. And so people recognized that having these symbols, this notation, was really advantageous. And that's one of the reasons why we who have this notation are better at numbers than fish. Now, what I've learned, this is to summarize what I've learned from Gelman and Gallistel. First of all, they taught me to distinguish internal representations of number and the words we use to count. This opens the possibility of counting in other species and thereby the possibility of an evolutionary account of how we come to know these abstract objects. We inherit a simple but specialized mechanism. They showed how the power of this mechanism can be increased by linking it to cultural tools, in the case of this particular book, counting words. And although they didn't go into this, they opened the possibility that mathematical learning disability is not a proxy for stupidity, as many people thought, but can be due to a domain-specific deficit in the system. Thank you. Just in case you were wondering.
Thank you, Brian, for an incredible tour of history and species and inspiration. I think we have time for a couple of questions.
Am I allowed a question?
Yes.
Go first.
It's just a basic one. Log snuck in, the most important assumption, addition.
Yes.
Without addition, you don't get iteration. Therefore, he assumed 1 exactly plus 1 exactly equals is also snuck in as 2.
Yeah.
So to say the only thing that's given is the generativity of 1 plus 1 plus 1 is to give away the entire assumption about that we have, which is that you start with the mathematical operation and exactly 1. And that's why you can say 10 is equal to 12 minus 2 is equal to 8 plus 2, 100 minus 90, etc. So you end up with an equivalence class within mathematics. And it seems to me that this seems to get lost, that many people working in the field are trying to generate the very operation that dreams the domain.
Yeah, I'm sure if Locke were here, he would entirely agree with you. I mean, he did use the word adability, so he didn't express it as clearly as you did. He didn't express it as clearly as you did, but I think he would have agreed with it.
I think it's really interesting how you could either have them be a strict empiricist or actually more like Rousseau. And in fact, I don't know, Brian, is your wife here?
Yes, it's right here.
Yeah. No, I mean the other one. Brian, a philosopher who has written a wonderful book on the fact that Locke, defaults on the empiricist side, and I guess it's Rousseau who defaults on the nativist side, both having been ambiguous all the way through. And so the question becomes why? But that's a separate issue.
That's it.
All right?
Yeah.
So I'll ask my question about the collective fish. There's
Yeah.
one result in one slide that quite amazed me. It shows that single fish, I think at 0.75 ratio, single fish performing at chance.
Yes.
And put fish together and suddenly they're above chance. That seems to me like getting something out of nothing, or 0 plus 0 equals 1. Do you have an account for that?
Do you see the error bars in that data? So, yeah, there are some good fish and some bad fish. And actually, one of the things we want to do now is we want to see what makes some fish good at this task, and some fish not so good at this task. And for this, we need a fish model, first of all, whose genome has been sequenced.
Were these zebra fish?
No, not yet.
Oh, okay.
Not yet. But we might. What we're hoping to do is zebrafish, so we can manipulate the genome and we can see it. Because we don't know that. I mean, one of the things that I didn't talk about at all is that when you're thinking about evolution, you don't know if there's been separate evolutionary streams for these different creatures, or whether there is a gene that is conserved for some kind of numerical task that we have inherited and we still use for that task. And we don't actually know the answer to that. We think we might have a clue when it comes to primates, but it's only a clue. We don't know what the gene is yet. Yeah, Mark.
Lovely talk. This is really out of my area, so but it's little bits of information that I picked up. So there are children, they're not fish, who seem to fall apart at once the numbers exceed their capacity. So there are 2 knowers, 3 knowers, and so on. And they fall apart, at least I've observed it with my own grandchildren, that once you exceed their capacity, they don't seem to distinguish between numbers outside their capacity, or numerons, or instances outside their capacity. I'm sure you have a good explanation for this, but you didn't discuss any of those kinds of data. And I'm wondering whether those data are wrong, or whether there's a good explanation for them in terms of the models you present.
Well, there are 2 real experts in the audience, the Gelmans, Rochel and Susan, who could speak to this issue more authoritatively than I can. I mean, both have shown that a child who, let's say, is 3 now, knows that 7 is a number word, but may not know exactly what that number word refers to.
It's not words, it's in terms of concepts. They don't, objects, they don't, if there are 3 here, which one would you like? 3 candies versus 2 candies. Or 3 candies versus 4 candies. Once you get beyond 2, they choose the 3 candies as easily as they will choose the 4 or the 5. At least my grandchildren did this. I don't think they're unusual, because I got it from other experiments. So I'm wondering about those kinds of data.
Well, apart from politeness, there might be another explanation. I don't know.
How, but it will take time.
Well,
actually, they're probably doing objects.
Mm.
It's ambiguous. When they're small enough, they could be doing objects as opposed to counting.
There are lots of people in this audience who've worked on this. So
Yeah.
Liz Brannon and
So
Sarah
I don't think we wanna
Cordes,
get
and
caught up on it.
Okay,
we
all
could
right,
have a whole
Sorry.
symposium.
No,
on
no,
it.
no, I think it's a very fair point, but I feel hesitant about talking about when there are so many experts who speak more authoritatively about it than I.
Thank you.
Thank you. That's